Hello, folks, and welcome to Rational Science. Why are we rational? Well, because just about everybody out there is irrational. And people say, well, Bill, that's just your opinion. What's rational to you is irrational to me. Well, that's not the way we do it in science. The way we do it in science, we have to define these key adjectives, find out what they mean. And so here we have a set of criteria for the word, for the adjective, right? Rational or irrational in this case. Treating concepts as objects. Number one, reification, concretization. What people do is they turn energy into a physical object and then they start transferring it. And they turn mass into a physical object and they start pushing it. They push the mass, they stretch the field, they accelerate the charge. All those are concepts. I mean, charge, what is charge? What is it? 1.6 times 10 to the minus 19 coulombs. Is that what you're accelerating? So yeah, it's when you reify concepts and turn them into objects, that's when we have a problem. And that's what mathematical physics does. Mathematical physics is in the business of reifying concepts. And in great measure, because they don't consider that, the mathematical physicists, they don't consider that as part of science. They don't consider it as part of physics. They say that's on the other side of campus. You got to go to philosophy of science or philosophy or whatever to do that. And it's the other way around, really. What we want to understand how this universe works. We want to understand how the invisible universe works. Mother Nature's invisible universe. We want to know how she does her, her tricks, her magic tricks, her invisible, intangible tricks. That's what we want to find out. And of course, you'll never find an answer to that in mathematical physics because, as Mr. Feynman, Nobel Prize of 1965, said, they've given up on that. Yeah, no kidding. They couldn't figure it out, so they gave up. Okay, so what does mathematical physics propose, and what does everybody out there essentially propose? Well, for the last 10,000 years, they've been proposing the same thing. Okay, maybe not that far back. I'm exaggerating a little bit, but here it is in a nutshell. What is light? Well, they say it's a bunch of flowing particles, and they're not really particles. I mean, they're not corpuscles like Newton thought of particles. They're not dust particles. They're not little balls. They're quantum particles. What's a quantum particle? Quantum particle is a magical particle. It has all these magical properties. In other words, it's not a particle at all. And just when you're going to touch it, just when you're going to grab it, it turns into a wave. You call it wave particle duality. And you say, well, okay, it turned into a wave. What's a wave? And wave is what you see there. It's a bunch of vectors, mathematical vectors. What's a vector? It has magnitude and direction. What the mathematicians have done is they illustrate vectors, mathematical vectors. All you're seeing there is magnitude and direction. Think of a number 5 with some direction, I don't know, and they're moving. Whoa, that's scary. That's very scary when that happens, it makes you tremble. And yeah, this is what everybody out there deals with. And so when you say, hey, this is all irrational, they say, well, again, go to the other side of campus. Talk to them, not to us. Okay, because this is part of the physical interpretation. That's what we're attacking because that's what physics is about, or was supposed to be about at least. And they stopped doing that a very long time ago. They gave up on that, like Feynman said. Okay, so they come up with this. This is their atom. And it's the ridiculous atom that Niels Bohr and Rutherford concocted, essentially, and then was carried on by everybody else. And what's irrational about that is, as you can see, there's a little bead, a blue one going around, and it jumps to a different orbital or different energy level. Then it pops back up, okay? So it goes from one region to the other. And the only issue that you got to ask here is, why doesn't that bead fly away spontaneously? What keeps it bound to the red proton? This is the atom, the hydrogen atom, right? What keeps it bound to the proton? That's all you got to answer. And if you can't answer that question, you can't even start your presentation. We will remove the microphone from the front of your mouth. We won't let you talk because you can't even start your presentation. You don't have an object with which we can follow your presentation. See, they explain, one, what you see at the bottom, they explain electricity with that. They also explain ionization. They explain quantum jumping. They all explain with this atom. And at the end of their presentation, they say, oh, by the way, that was in our atom. We cannot imagine our atom. That's what they tell you. And so, yeah, what you see is what you get. And what you get is not what is. In other words, what you're supposed to do if you're a proponent of that atom, that planetary atom, which everybody, 100% of the people use this and illustrate this. Don't take my word for it. Just Google, in the images, the quantum atom, that's what you'll see. You won't see another one. And you say, well, why does the bead fly away? That's all you got to answer. It's that simple. You can't answer that question. You can't start your presentation. You've got nothing to share with the world. And here is the carbon atom I showed the other day. This gives you an idea here of the more sophisticated atom they'll teach you in college. And what do you see? You see all these little flies in there. Those are the beads, the electron beads. And they can't escape the balloon because those balloons are like regions that somehow hold them back. These are the orbitals, as they call them, bunch of orbits. And you say, what are those, balloons? And they'll say, no, those are not balloons. So what are they? How can they, is that a fence? I mean, does that prohibit, does that impede, does that forbid the bead from flying away physically? And of course, they treat that mathematically. They're not going to treat it physically because they have no physical interpretation for those regions. And if you go, look it up, don't take my word for it, look it up on YouTube and you'll find that all people who explain these orbitals, they'll explain it with balloons. They tie all these balloons like clowns do, and they say, well, this is what the orbit, the p orbital and the s orbital and so on. And you say, well, are the orbitals balloons? And they say, well, no, you're not supposed to take that literally. This is an analogy. Then why doesn't the bead fly away? Just as simple as that. If you can't explain that, you can't introduce the orbital just at random and say, oh, I'm going to introduce an orbital just for the sake of my presentation. You can't do that. It's ad hoc. What do we propose instead? Well, we propose something a little different. This is how the atom is constructed, really. It's a physical entity, not like in mathematical physics, which it's an abstraction. We have two physical threads, and they twine around like DNA, and they form this rope, which is going to be the mediator of light, and they converge upon our atom. Okay, you can see there they converge upon the edge of the atom, and that red line, that red curved line, that's the electron shell. It's weaved by every rope coming from every atom in the universe. All atoms in the universe are physically connected. One thread goes through the center of the atom, and from every atom in the universe, we have one donation, one thread, and that forms that proton star. And the star is encapsulated by a membrane, which we call the electron shell. And there on the bottom left, you see quick 2D and 3D versions of what we're proposing. Okay, so that's in a nutshell our atom. What can we explain with this atom? Now we showed you the physical object. If you have questions, well, you can ask about them, but at least you know what we're presenting. And we're not going to say, well, that's not our atom. No, that is our atom. Okay, so what you saw is what you get. Okay, that's what you bought. Okay, you don't have to believe it. You're just supposed to understand it. Okay, so what is light? Well, light is this. The atom expands and contracts. Okay, you have the 2D and the 3D version there. And what it does is torque the rope. And the torsion along the rope is what we call light. That's why light is so fast, because light is not a 2D transverse wave that goes up and down, as Fresnel said in the 19th century, and James Maxwell. No, what light is a torsion, a 3D torsion along a physical mediator. Okay? And you may say, well, I don't know about that. But one thing we can explain with that is speed. Why is light so fast? And I made a little, I call it my rope machine. It's a torsion machine. And I took it to one of my presentations. I don't know if I presented this in the past, but let me just show you this. Okay, if I can find it here. Where is it? Here. And this is my torsion machine. It's a rope that's twirling, and the signal goes in both directions, in opposite directions simultaneously. And this is going at very slow speed, but light really, a torsion just is the fastest thing you can imagine. It really is. In fact, I tried to film once. I put 2 clothespins on a rope, and with a camera trying to film this, and I touched one to see if I could see when the other one moved. It's like instantaneous. You can try it at home, always in the presence of a relativist, okay, because dangerous experiment. Okay, and what else can we explain? Well, we can explain why light also travels always at a constant speed. Okay, and here it is. When you shine light through a prism, okay, what you're going to get on the other side is different colors. What are colors? Well, they are different link lengths of the rope, and you can see the equation there, the wave equation, C equals frequency times wavelength. Okay, and when you increase the frequency, the wavelength goes down, and vice versa. In other words, they're inversely related. Okay, inversely proportional. And so all we do with the rope is just exchange frequency for wavelength. There's no way, never an increase in speed. Here, let me give you a for instance. Okay, here you have a rope. Get in the center here. Okay. And you see what, maybe 3 links there, okay? And for that amount of rope, that's between my 2 fists, and those represent the atoms, right? Okay, what happens when you torque the rope at a higher frequency, right? We're going to get higher frequency here, okay? And now we have what? More links, but each link is shorter. C equals frequency times wavelength is the equation of a rope. What have we done? We've shortened the wavelength, in this case the link length, and what we have is more links, more frequency. C equals frequency times wavelength, which is the wave equation. Why, the speed of light, they say in a vacuum, no, it's always, is the equation of a rope. Okay, and that's what it is. So we can explain all these with a rope model. Okay, and it's a physical model. Hopefully, Mother Nature does her things out there with physical things and not with abstract mathematical concepts such as energy and fields. Okay, so this is where the problem is. These people are using concepts, and then they say, well, we didn't mean it. Yeah, no kidding, you didn't mean it. Okay, so summarizing, here's the difference between the rest of the world and us. And what these people do is they have all this ether particles, and when they want to use a wave, they say, well, it's the vibration of the ether. So there you have your wave. It's, what is it? The vibration of those particles. What do we propose instead? We propose that all atoms in the universe are physically interconnected. They are physically interconnected. What interconnects them? The electromagnetic rope that binds any 2 atoms, and which becomes the atoms, so it's a long string. It's a single thread in all of space. That's all it is. And that thread moves through every atom in the universe and builds the atoms and builds the ropes that interconnect them. That's the model. Okay, so you can see we're a little different than everybody else out there. Okay, and yeah, the ether is what everybody else uses. And you don't have to take my word for it. Let's go with a little bit of authority, which is what people believe out there. And here's authority, okay? Mr. Laughlin, Nobel Prize in 1998. And what did he say? He says, a modern concept of the vacuum of space, confirmed every day by experiment, is a relativistic ether. Okay? But we do not call it this because it is taboo. Yeah, it's the ether. I mean, what is space-time? Space-time is a bunch of events, right? And each event, what is an event? It's a point in space-time. It's a tongue twister. It goes back and forth, right? And so when you take all these points and put them together, you have a sandbox, right? And what is a sandbox? Well, it's ether. That's the ether. So the ether is a sandbox, but somehow they have all these particles just moving. Okay, and okay, that's the ether, and we've never abandoned the ether. We've had the ether for the last 3,000 years. No one has ever abandoned ether. Robert Hooke used it. Huygens used it. Newton. All these folks used the ether. They were all believers in the ether, that there was this background of particles, and it was waving. Newton said it went straight. The other guy said it was waving. But the point is, they all relied on the ether. And today there's no difference. Quantum calls it the ether. They call it the false vacuum. They talk about particles coming in from space, separating into positive and negative particles, recombining, going back to form nothing, space. Just magic, pure irrationality.